So in this video, I want to explain to you how the code works for implementing the packing and the unpacking algorithm for the 2 and 4-bit quantization. So I'm going to follow directly from the example that we had here where we were packing these numbers that had already been quantized down into a 4-bit range into these two numbers that would then be put into this tensor right here. I'm going to show you how it works in the code. We're going to make use of two things. We're going to have to make use of bit shifting, so we're going to have to shift bits, and we're going to be doing bitwise OR operations, and for the unpacking step there's going to be a bitwise AND operation. So I'm going to explain that to you here. So first and foremost, what we're going to do is we're going to have this final quantized tensor that it's going to be our goal tensor, right? Because inevitably what we want to do is we want to get to this tensor right here, where we have 144 and 251 that are these, it's a packed representation of all of these numbers here. And so what we're going to do is we're first going to pull out those numbers. And so all of these right here, the variable names, are chosen directly from the code so that you'll know what you're looking at when you look at the code. And so we have this array here that's going to be a row. The code that I implemented is meant to run on a multi-dimensional tensor with many rows and many columns. And so we're only going to have one row in our example. And this row has the numbers 0, 9, 11, and 15. And then we're going to have this quantize row, which is supposed to be this row packed into these two bytes here. These two numbers, and these are their bit representations. So we're going to start off with an empty array. Well, it's not an empty array, but it's a zeroed array. These numbers are just 0 right now, and we're going to fill them in. So I'm going to start with the number 0, right? Because the goal is we want to take these two numbers right here, and we want to fit them into this bit array right here, and then we want to take these two numbers here and fit them into this bit array right here. And so that is what we're going to do, and we're going to start with the number 0. And now the number 0 represented as a bit array is just all zeros, right? And what we're going to do is we're first going to, we're not going to shift 0 at all. We're not going to do any bit shifting on 0 because what we want is that we want, remember we want 0 and 9 to be packed into here. And if you remember, 0, okay, takes up this right side. We want to pack these 4 bits that represent 0 into this right side of this one. Just as a reminder, you can see here that 0 gets packed in here, and then 9 right here gets packed in here. And so that is our goal. And so what we're going to do is we're going to do a bitwise OR operation. We're not going to shift any bits here. We're just going to do a bitwise OR operation between this bit array and this bit array. And the output of it is going to replace this bit array. Now, bitwise OR looks at each cell, each entry, and each respective entry in each array. And if either of those entries, either this one or this one, if either of those are 1, then it's going to replace this cell with a 1. However, none of these are 1. They're all zeros, so bitwise OR is just going to keep this exactly the same, and nothing is going to change. That's not going to be the case for the number 9. So for the number 9, we now move on to the number 9. We're going to change this to 9. And now the bit representation for 9 was a little bit different. Remember, it was not that, it was this, right? And we are going to do bit shifting on it. And so what we're going to do is we're going to shift this right here, because remember our goal was to have 9 packed into this side. We're going to shift this right here 4 cells to the left, right? So this one's going to be put right here, this one's going to be put right here, this one's going to be put right here, and then this one, I know it's a little bit blurry, or a little bit mixed up, but this can be put right here. And that's all going to make sense in just a second. So this right here is going to be put here. And then when we shift all of the entries here on this side, all of this gets zeroed out. and there's nothing left there. And then we do another bitwise OR here. Now, you can tell that this side right here, all these respective entries are going to be left 0 because none of these are 1. But you can tell that this one right here has a 1 and this one right here has a 1. So both of these are going to be changed to 1. That one's going to be 1 and then this one's going to be 1. And then we're going to be left with this side of this bit array being equal to 1, 0, 1. And as you can tell, this number right here on this side represents the number 144. Just a reminder, remember this was our end goal bit array, and then we have 144 here. And so we're already off to a good start. Just shifting bits and doing bitwise OR. And the same thing continues for bits 11 and 15. Remember, we want 11 and 15 to be packed over here. We want 11 to be packed into this side and the right side. And then we want 15 to be packed into this left side here, right there. And so what we're going to do is now we do the same thing with 11. This is now going to be 11. And 11, remember it's in 4-bit notation, so we're only using these right 4 bits. Remember 11 is represented as 1, 0, 1, 1. And so let's do 1, 0, 1, 1. And remember, we want 11 and 15 to be stacked or packed into this final number over here, right? This bit array over here. And 11, we really want 11 to be here. So we're not going to shift 11 at all. We're going to keep it the same. And I know this is a little off, but remember we're doing a bitwise OR operation. And you can tell that these respective entries right here are 1. And so have a 1. One of them has a 1. And so for that reason, we're going to replace these right here with what's right there. And then these are all zeros, so nothing gets replaced here. Now we're going to we're going to bring over 15. We are going to shift this. So when we shift it, these ones are going to be put over here. And then this is all going to be 0. So this doesn't change, but here you can see that the bitwise OR between each of these respective entries is going to be 1. So let's change this to all 1s. And this number right here, right, which refers to this entry here, is the same that we got over here. All 1s here, and then 1, 0, 1, 1. And that bit array represents the number 251. And so this right here is going to be 251, right? And so, and then finally, last but not least, we're going to take this quantized row and we're going to replace the only row we have in our example, but we'll do a multi-dimensional example. You'll see that in the code. And obviously, this is the representation for these two numbers as well. And our packing step is completely done. And so if we go over to the code real quick, so I'll explain a little bit to you, but I can't explain everything because we're running low on time. But here, this is the bitwise OR operation in Python between the quantize row that we have here and then the row from our input tensor. And then this is how we do bit shifting to the left. And so why is the first number not shifted to the left at all? Well, because when we first hit that first number, remember it was 0, it was 0 and 11 in our case, j is equal to 0. We're at the zero iteration of this loop. And so anything bits times j is just going to be 0. I wish I had time to explain this to you, but maybe in a later iteration of this course, I'll explain it to you in more depth. But I just want to explain those two parts. And so if we run this code, we'll get 144, 251 as our output quantized tensor. And then now we need to move on to the unpacking step. So the unpacking step is in reverse. Remember, in the packing step, we had this final quantized tensor. The goal was to have 2 entries, right? Because, it's 4 bits. We wanted to represent 4 numbers with 4 bits each. And so this is 8 bits, this is 8 bits, this is 8 bits, this is 8 bits, so it's 16 bits in total. And so unpacking is the opposite, right? So we're going to start with 4 entries because we want to end with 0, 9, 11, and 15. we're starting with this 144 to 251. And then we start with 144, and our row, you know, if we have these four numbers that we want to replace with 0, 9, 11, and 15, is 4-bit arrays, 4 8-bit arrays, all zeros to start off with. And then we take, what we do is we take 144 and we do a bitwise OR between it and this entry. And then obviously, since we know how bitwise OR works, this side right here is going to be 1001. And also we'll say we're not shifting to the left now, we're shifting to the right. And so what we're going to do here is 144, we're going to move it over again, and then now we're going to shift it 4 bits to the right. I said it was the opposite, it really is the opposite. And then so now once we shift it to the right, we're going to do a bitwise OR between it and the entry here. And then that's going to be that. And then now we change up. We now are going to be working on 251. 251 is represented as 111, 1011, right? Yeah, 1011. We're not going to do any shifting to the right. We're just going to do a bitwise OR between it and the entry right here. Remember, on the first iteration, there is no shifting at all. Right, and then we move it over to the other entry. And then now we do some shifting. We shift it 4 bits to the right. That's going to move this here, and it's going to zero everything that's left over here. We do a bitwise OR here, and then this right here is 111. Finally, what we're going to do is we're going to create a mask. And so this mask is only going to grab, what it's going to do is it's only going to grab off those last 4 bits to the right, because we want to get back to our 4-bit representations of 0, 9, 11, and 15. And what we do with this mask is we go entry by entry, and we do a bitwise AND operation. So in order for this one right here to be 1, both of these, its respective entries need to be 1. And so that's not the case over here with it in the mask. So that's going to be 0. And then this right here, neither of both of these entries at any of these respective entries, it's a little confusing, is 1, right? All of these are 1, but all these are 0. And so this is going to be 0 with our bitwise AND operation. And then we move the mask over here. And we only have a 1 for bitwise AND in these two entries right here. And so they're going to be left the same. Here, we're going to do a bitwise AND. Neither of these have 1s in each respective entry. These have 1s, these have 1s, these have 1s, so they stay the same. This one has a 0 and a 1, so it's going to be 0. And then here, we're just going to keep everything the same because all these are 1s, and that's what we're left with. And then now, each entry here represents 0, 9, 11, and 15. And then we're going to replace our final tensor, the row that we're doing operations on, with the output. And here, this is going to be its bit representation. And then we return, oops, zoomed out a little bit. And then we return this tensor right here. And then we do our normal dequantization back to the 32-bit precision. And so all that is down here, this is how we create that mask. This is how we do the OR operation again. Remember, we're shifting to the right, so we have these two arrows to the right. And then this is how we do the bitwise AND with this symbol right here. So if I run this, I get this tensor. And then this right here computes quantization error. And so you'll see we have 144 on here. The quantization error is really high. And so what I want you to do is I want you to run the rest of this notebook, because we're running out of time here, to see how the quantization error does on this. And then I want you to compare that to the other higher bit precisions just to see how much loss there is. But that's how we do the packing and unpacking for the 4-bit quantization.